We are now equipped to compute probabilities of genotypes in the filial generation. The conditional probabilities point the way, and they point to a natural partition of the probability space. Pause for a moment and think about how would you set up an expression by partitioning the probability space. A little introspection might have told you that it would be natural, completely natural, to partition the space based upon who the parents were. And that immediately opens up the problem and gives us the answer in one fell swoop, and all will be over bar the shouting and just a smidgen of algebra. So let's begin. What are the chances of obtaining a child whose genotype is normal and homozygous, in other words, two uppercase A's? Let us call this probability U prime. So in other words, U prime is the probability that the child's genotype is two uppercase A's. We naturally condition on each possibility for the parental genotypes. Both parents are normal and homozygous. The father is normal homozygous. The mother is a carrier, heterozygous. The father is a carrier. The mother is normal and homozygous. Both parents are heterozygous. This is total probability, the magic of additivity. Once you find the right way to break up a problem, it becomes transparent, even trite. Now, the expression took more time to write than to imagine. We could just as well have obtained this by looking at the figure on the upper right of your screen. You want to get the child genotype being normal and homozygous. Look up all the arrows that enter it. There are 4 possibilities, and sum over those 4 possibilities. The weight on an arrow is the conditional probability, multiply by the probability of the a priori probability of the parental genotype, and sum. This is all there is to it. And in this case, of course, we could just look at our tables and write these numbers down if we wished, and we get an algebraic expression. This is simple. The denominator is the square of 1 minus w. It's common to all the terms. We collect it, collect the numerator, write it down, and now recognize that in the numerator I've got a whole square. U square plus twice uv plus v square is inevitably u plus v the whole squared. In the intermediate step, I've got a square in the numerator and the square in the denominator, and it will be really convenient, trust me, to rewrite it as simply u plus v over 1 minus w, the whole square. A square relationship has emerged from this algebraic mess. Let's hold on to that for a moment. Right? It's going to turn out to be particularly informative and illuminating and useful. But right now we just got a square, and for our purposes, we've done the problem. Given the ratios u to 2v to w for the genotypes in the parental generation, given that the infected individuals cannot mate, given random selection and random mating, the probability that the child's genotype is normal and homozygous is simply u plus v divided by 1 minus w, the whole squared. Okay, so far so good. If nothing else, it's got the virtue of being simple. What about the probability that the child ends up being a carrier? The child has a heterozygous genotype. Again, to be consistent, we're going to call the probability for the heterozygous case in the filial generation twice v with a prime to distinguish it from the corresponding situation in the parental genotypes. So twice v prime is the probability that the child has got a heterozygous genotype. And we do exactly the same thing. We're going to condition based upon the 4 possibilities for the parental genotypes. And when we do that, we realize that the case where both parents are normal and homozygous cannot contribute, because in that case neither parent can proffer a lethal gene. And now we've got another algebraic system. Again, it is simple. The factor 1 minus w the whole squared is common in the denominator, and each of the fractions 2 is common in the denominator. Put everything together, and we've got another simple expression. And it will again be convenient, trust me, to realize that in the numerator, the factor 2 is common, so you can factor it out. The factor v is common, you can factor that out, and we'll separate it into twice a product of two fractions, u plus v over 1 minus w and v over 1 minus w. The last case follows exactly the same pattern, but it's even simpler, because the child can have the lethal genotype if and only if both parents are heterozygous and both parents proffer the lethal gene. In this case, 3 of the possibilities vanish, leaving simply the last one. Write it down, and we find again, oh, there's a beautiful square. We get v divided by 1 minus w, the whole squared. At this point, you see, all the probability has been exhausted, but the story has not been exhausted. The results are elegant and simple enough to suggest that there might be some information that is hiding in these patterns. Let's try to look at this more carefully. And the way we're going to do this is by setting up the parental genotypes on one hand and the filial generation on the other, and looking at the probability numbers as you go from one generation to the next. Here's what we know. In the parental generation, on the left of your screen, we start with an original population where males and females have genotypes normal, homozygous, heterozygous, or lethal in the proportions u twice v w. If you want, for definiteness, think 60%, 30%, and 10%. Of that subgroup, lowercase a genotype individuals are forbidden from mating, sadly. And so, in the mating subpopulation on the parental side, the normal homozygous individuals appear in proportion u divided by 1 minus w, and the heterozygous individuals appear in the proportion twice v over 1 minus w. And if we look at the genes these individuals proffer, then individuals in the mating population in the parental generation proffer the dominant normal gene uppercase A with a probability p, given by u plus v over 1 minus w, and proffer the lethal gene A, little a, with probability q, given by v over 1 minus w. Now, we'll use the same notation for the filial generation on the right of your screen. In the filial generation, the genotypes appear in proportions, we'll use the letters u, 2, v, and w again, with primes on them now, to remind ourselves that we're dealing with the next generation. When that generation mates, then again, lethally infected individuals cannot mate, and the remaining individuals, normal, homozygous, and heterozygous, mate in the proportions u prime over 1 minus w prime and twice v prime over 1 minus w prime. And finally, in that mating subgroup, in the filial generation, the dominant and the lethal genes appear in the proportions p prime and q prime, exactly as before. Now, the whole point of the exercise is that the probabilities on the right are conferred by the probabilities on the left by the relations in the middle of your screen. This is what we discovered. This is what total probability gave us. It looks simple enough, but further simplifications are immediately at hand. Take a good look at the screen. Does anything jump out at you? If you looked at the lower left of your screen, you'll realize that the probabilities p and q in the parental generation appear to have the same form as the expressions for the filial genotype probabilities in the middle. And indeed, we notice, quite serendipitously, these beautifully elegant results. The normal homozygous probability for a child is simply p squared. The square of the probability, or the proportion of the normal gene offered in the mating population. The percentage of the population which is heterozygous in the filial generation, twice v prime, or at least the expected proportion of this population, the probability of getting a heterozygous child is twice pq. And the probability of getting a sadly infected child, w prime, is simply q squared. Oh, this is a remarkable and beautiful and elegant simplification, and this is going to lead to profound consequences. So let's now step back and ask the following basic question. Recall that the lethal gene, little a, is in the parental mating population with proportion q. It is in the filial generation's mating population with proportion q prime. Of course, q prime is related to v prime and w prime, which in turn is related to u, v, and w. Well, what is that relation? Well, let's write this down. So q prime is v prime over 1 minus w prime, but twice v prime is twice pq, and therefore v prime is just p times q. And w prime is q squared. So we get pq over 1 minus q squared. Now, an elementary factorization will tell you that 1 minus q squared in the denominator is 1 minus q times 1 plus q. Very well. But we realize, wait a minute, that p plus q is 1. And therefore, 1 minus q is the same as p. If you cancel 1 minus q in the denominator with p in the numerator, that leaves you a very elegant and simple result. We could hardly ask for more. The fraction, or the expected fraction, if you will, of the lethal gene in the mating population in the filial generation is given by the ratio of the expected fraction of the lethal gene in the mating population of the parental generation divided by 1 plus q. A little rejiggery will make it even simpler. Simply take the ratios. Take the reciprocals of both sides. So, if you look at 1 over q prime on the left-hand side, that is the same as saying 1 plus q over q, which is the same as saying 1 over q plus 1. Or in words, we can put it very succinctly. The reciprocal of the lethal gene in the mating population in the filial generation is given by the reciprocal of the proportion of the lethal gene in the parental population plus 1.